Ramanujan for G is now available on the Google Play Store. Try it out for free.
So hi students. So today we are going to start first with a little bit of a. We're not going to do a review today because usually I always start with the review. I will go to the review later. First, I am going to introduce you to the idea of how questions are to be solved. Okay. Now, wherever you can get MCQs from any 100 places. I will show you all the books that we use. Have a lot of free books also we use. We go here and there. A lot of websites. Today you can go many places to get questions. Okay. Now, the most common place is to go to previous year's NEET, previous year's JEE. If you go to previous year's NEET, previous year's JEE, then you will get, slowly you will build success. Okay. Now, students who buy HC Verma has solved problems also. HC Verma has solved problems. And every chapter he will solve some problems. Then he will give you some questions. So that is one place to go. NCERT textbook has questions. You should do those. And then go from there. So let me get going with a couple of questions here. So these are all questions. Let me share my screen. Okay. So see, I will take some time with the questions. You should not feel time pressure initially. So I am going to also take some time to solve these questions. Okay. So 1 minute. So we saw all these slides last class, right? Everything we have done here, So now this question, okay? See, this is a typical JEE question. All the graphs below are intended to represent the same motion. One of them does it incorrectly. Okay. So he's saying this, if you draw V versus T curve, you draw A versus T curve, you draw P versus T curve, draw distance versus T curve, etc. Right? All of them, he's saying that one of these somehow has gone wrong. So So welcome. So we are doing some questions today. That's the goal. We're starting with some questions. So now these four curves, this is the first question we are looking at. These four curves are, there is velocity, velocity versus position, right? Now, the velocity versus position, if you look at, there is, you always typically start from first principles, okay? So if you have position versus time, right? So let us say you had this curve, right? Let's say this curve, is an inverted position versus time curve, right? See, this curve and this curve, 3 and 4, right? They both represent classical constant deceleration curves. Okay, I'll tell you why. When you have constant deceleration, right, in one-dimensional motion, if you had constant acceleration, it will be the P versus T curve will be a upsloping parabola, right? Now, if the P versus T curve is an inverted parabola, that is a deceleration curve. Okay, so S is equal to Y is equal to X square is what? Parabola, right? So S is equal to UT plus half AT square, parabola, right? But if the A is a plus, the body is accelerating, right? If the body is accelerating, it will be a upsloping parabola, right? So here, 3 and 4, both represent, 4 is V versus T, right? If V versus T is a straight line, right, that means it is a decelerating body, okay? What happens in deceleration? Like when the train is coming to a stop, when you apply the brake, right, it is going to go like that, right? Or if you throw a ball, right? See, I'm going to throw this, right? Oh always bring something that is easy to throw. I don't want to throw my cell phone, Okay, I'm going to throw my glasses. Okay, so now what happens, right? So the initial, let us say, upward velocity is positive, right? So initial velocity is going up, it stops, right? At that point, the velocity goes to zero, and then it turns around and goes negative, right? So this is constant acceleration curve. If you make this as negative, right? So then it is decelerating, okay? So it slows down, stops, and then decelerates. So that is exactly 4, okay? 3 is the position versus time curve corresponding to 4, okay? So now the question is, what is the V versus P position curve? V square equals U square plus 2AS. What will that look like corresponding to this, right? So now if you see this, right, it goes up, the velocity goes up, it goes to zero, then it decelerates, right? Now, uh, uh, but remember that this is not time, right? When the position is, let us say if you take the position, when the position is maximum, the velocity is zero, right? Now you see that that is true there, right? This is not a time curve, okay? So now it is retracing its path, okay? So when the velocity is maximum in the upward direction, that is when you first push it up, right? So at that point, you have the position, as if you said this position as zero, then the velocity is maximum when you first push it, right? Then when it comes back, it is the same amount in the negative direction, okay? So 1, 3, and 4 clearly represent the same thing. So if you do this, right, you will have 3 inverted parabola, right? It is going up, the position goes up, it goes to maximum, then it reverses itself and comes to zero. When it goes to the maximum, the slope of the position versus T curve goes to zero, right? So 3 and 4 are very clearly the same. 1 is also the same as 3 and 4. Okay, if you look, because it is a velocity versus position curve. Velocity versus position curve, notice that it is a little tricky. Okay, so 1, 3, and 4 are all the same motion. Okay, one of them does it incorrectly. The answer is 2. Okay, so please, when you look at these graph questions, they are very tricky. You must be careful. You must know, in constant acceleration, constant deceleration, firstly, what all happens. And then you must also understand this is basically, if you understand derivative, one is the derivative of the other, which is the integral of the other, etc. These position versus velocity, velocity versus position, distance versus time, acceleration versus time, they will all be constant, right? So if you look at the acceleration versus time for this curve, it will be like this, it will be like this, and it will be negative horizontal, okay? Constant deceleration, okay? Which means that the acceleration is negative, okay? So that will be the 4 curve. So 2 is the incorrect curve. I took long time. You won't get so much time. NEET, remember you have 45 questions. You have to make time a little more for physics, right? I don't know if you listen to Professor GK, but that's the idea. Okay. Okay. So that first question dealt with kinematics. We have taken care. Now this question is dealing with forces. Okay. So once you see pulley, this, that, right? We just yesterday, last class only, we looked at the pulley problems, right? So pulley means you must do calculations. Okay. But if you can solve these, you will have no problem with NEET also. NEET questions you will have. JEE questions you may take little more time. NEET question may take less time. But right now we are not thinking about time at all. We're thinking of just getting the questions correct. Okay. So what do you need to do? Two masses 5 and 10 connected right? Inextricable string or frictionless pulley. Okay, so they've already drawn everything for you, right? The coefficient of friction on the horizontal is 0.15. The minimum weight m that should be put on the top to stop the motion. Okay, so they are saying that, see, this is a standard, what is that? Pulley problem, right? But it is not. It is not. See, standard pulley problem is called Atwood machine. There are two solutions for this Atwood machine. Last time also we looked at m1 minus m2 by m1 plus m2 times g. That is when there's no friction. But here there is friction. Okay? So if there is friction, you must write the equation. Okay. So you look at this m, right? You look at this m2, right? You add m plus m2. Okay. So m2 is 10. So 10 plus m. If you draw the free body diagram of m and m2 together, that is the clever thing you have to do. Okay. n plus m2, right? In the vertical direction, m plus m2g equals n, right? In the horizontal direction, t minus 0.5 m plus m2g, right? T minus 0.5 m plus m2g equals 0 because it's not moving, right? The tension is as much as the friction, right? So T equals m plus m2 times 0.1 g times 0.15. Okay, so how many unknowns? You have two unknowns, right? So now you have to rely on the other equation, right? So the other equation has T and m1, right? So T equals m1g. Okay, so then you plug that into the equation, right? So m1g is what? 5 times 10, 50. Let's say you put g as 10, but you should do 9.8. If you have calculator, there's no calculator, use 10, right? So 10 times 10 is 100, right? T is 100, right? So 100 equals 0.15 times, not 100, 50, 50. M1 is 5, right? So 50 equals 0.15 times 10 plus m times g. Okay, so if you want, you can cancel the g and then make it 5, right? So 5 equals 0.15 times 10 plus m times times 10 plus m, right? So the net answer you will get, right? The middle weight, you calculate the mass, right? And then from that, you use the corresponding results. So 0.15 times 10 is 1.5, right? 1.5 times 1.5 plus 0.15 times m equals 5 times equals 5, right? So that you calculate and correspondingly you will get a result. Okay, so try to do the calculation, you will end up with a result. Okay, so this is also a simple problem. Okay, but you must draw the equations, write the formulas, and draw the free body diagram and solve for the solution. Okay, so not at all difficult. You just do the maths, you will get answer. Simple algebra, you get the answer. Notice it is two equations. The big one has two equations, two unknowns. Second one gives you one unknown, right? And then you plug it back. So you just have to do algebra, right? Simple algebra. Once you know that, you should take m and m2 together. That's the only thing that you have to learn. Okay. Okay. Now this question is also very simple. Okay. A particle is moving with a uniform speed in a circular orbit of radius r. Okay. So here's uniform circular motion, circular orbit, right? See, this is a standard gravitation question, okay, of radius r in a central force inversely proportional to the nth power of r. Okay, now he is complicating it for you. Okay, so what is he doing? He's saying, see, normally, right, you know t square is proportional to r cubed, but then that is happens when you have t square is proportional to r cube is when you have the nth power is 2, right? The second power of r. The central force in gravitation is what? Gmm by r square, second power of r, right? So if the period of rotation of the particle is t square is proportional to r cubed, right? So he's trying to say, but if I make it nth power, what will happen? So he's trying to see if you know how to derive this equation, right? So how is this equation derived? Gmm by r square equals m omega square r, right? And omega is 2 pi by t, right? So then if you rewrite it, it will end up becoming r cubed. T square is proportional to r cubed because you have r square is the denominator on the left side and you have one r on the right side, right? So and then you have omega square which becomes 1 by t square, right? So you end up with t square is proportional to r cubed, right? So now instead of gmm by r square, you have gmm by r to the power of n. Then you will end up with t square is proportional to r to the power of n plus 1, right? So now you will end up with t, if you do the square root of both sides, you will end up with t on the left side is proportional to r to the power of n plus 1 by 2, 3. Okay, very simple. All right. So why I took some time to solve these three problems is to tell you it is not difficult. If you slowly pick up the material, you learn it well, and you go about solving problems. Okay. So these questions, when you solve them in the exam, right? You should have, if you have built enough confidence, you have tried along the way, they will become easier and easier and easier, and you will get more and more comfortable, and also with time. Okay, so you build confidence, build strength, etc. Okay, so please continue to pay very good attention to solving problems. We do one chapter, you then have to take it upon yourself. We are going to be readying the question module for our app, and it was going to be available, so that when after you study, you go to the app, you do the self-assessment yourself. Okay, see, with JnanaMarga, we will help you, but we are not. Finally, the student, when comes time for the exam, the student only has to sit for the exam. No teachers will come and help you anytime, right? So that's why you have to be very good with this. All right. So moving on to today's material, let us get going with the new chapter. Okay. So what I am going to ask you to do is go do more problems. Okay. Your kinematics is there, dynamics is there, force is there. Do more problems involving these questions. Okay. Uniform circular motion. Learn the material. Listen to the lectures. Download the app and try it. Learn the material from there. Then do self-assessment. Okay. Keep going forward. You will be very soon feeling the confidence and being ready to do more and more problems. Okay, that's what we are here for. All right. So today I'm going to start a new chapter. So we kind of little bit get going. Okay. I hope 1 minute. It's taking a little bit time. All right. So here we are. So work, energy, and momentum. Okay. So now these are actually very different ideas. Okay. Work and energy are very different from in the conceptually compared to the momentum and other things. Okay. Now, I'm going to introduce this firstly in the context of collisions, but work and energy is an ocean. Okay, work and energy is the essence of so much of physics. Okay, so you must pay very careful attention to learning about work and energy because they are not so straightforward concepts. Although everybody knows what is energy, I am always getting these WhatsApp about Nityananda explaining work and energy. So it is firstly, but you have to learn these things in careful detail. Okay. Now, rigid body, the linear distance between any 2 points of the object remains constant or changes negligibly through the motion regardless of any external forces. Okay, so notice this definition of a rigid body. Rigid body, most of the bodies in most of the problems in physics you deal with are rigid bodies if they don't tell you it is a rigid body. Okay, unless they tell you it has deformed and become, like a putty or like a ice cream or like a banana, right? Unless they tell you it's one of these things, it is it is definitely a rigid body. Okay. Now, the most common three types of motion we deal with, that is movement in the context of this, is translation, where there is sliding. Okay, where you have all this free body sliding, right? Rotation, right? Rotational motion we have not dealt with, we'll be coming later. Translation plus rotation, like when a car is moving, right? When a car is moving, the wheels are rotating, right? Or like the motion of a top is only rotation, pure rotation, right? Then in between the two, then there is translation plus rotation, which is like the ball rolling down an incline, car rolling down a plane, etc. Okay. Now, in between this, there is also uniform circular motion. Okay, uniform circular motion is a kind of translation, but involving something revolving around something. Okay, so that is a little different from rotation. We will deal with that also. Okay, so we will be dealing extensively with rotation because that's a slightly tougher subject. But first, you must get the basics very well. Okay, the most important laws are Newton's. Okay, everything is dictated in mechanics by Newton's laws with respect to everything you learn in for class 11, class 12. You will be doing modern physics. They will keep telling you these things. Maybe they don't apply properly, right? Don't worry about that. As long as it's a mechanics question, you apply Newton's laws, you apply work, power, energy, and everything will work out. Newton's first law always applies. Okay, body in a state of rest or uniform motion, unless there is a force, it will continue to experience rest or uniform motion from the point of view of someone who is in an inertial frame. Okay, Newton's second law: in an inertial frame of reference, the net force is equal to the mass times the acceleration, or differently stated, the rate of change of momentum is directly proportional to the force applied. Okay. Now, let me explain another concept in the context of Newton's second law as an aside. Okay. There is this concept called impulse. Okay. Virat Kohli is batting. Okay. Virat Kohli is batting. Then Mitchell Johnson, not Mitchell Johnson, Mitchell Stark is bowling. Okay. Virat Kohli is batting. Mitchell Stark is bowling. He is running, and then he bowls the ball. Right. Virat Kohli takes a front foot step, and then he plays a shot. Okay. Now, the ball is coming, it pitches 150 miles an hour. The commentators, oh, what a fast ball, 150 miles, not 150, 150 kilometers per hour, right? 150 kilometers per hour. Mitchell Stark is bowling, right? Virat Kohli hits the ball, right? Then now, for a very brief period of time, the ball is in contact with the bat. Okay. During that period of time, what happens to the ball? It hits the bat and it flies off into the cover boundary. Okay. It is outside the off stump. He has driven the ball. It has gone to the cover boundary. Right. Now, so uh, how long is the ball in contact with the bat? Very short period of time. Okay. Now, during that period of time, what Virat Kohli has done to the ball is he has applied a force for a short period of time. When a force is applied for a short period of time, you are uh, producing what is called an impulse. FDT is called impulse. Integral FDT is impulse. Over a very short period of time is impulse. Okay. Now, what happens due to the impulse? The momentum of the ball changes. Okay. Now, when you throw a ball against a wall, right, it bounces back. For a short period of time, it is hitting the wall and then it is coming back. Okay. So now we can say that during that short period of time, there is a impulse applied by the wall on the ball or by Virat Kohli's bat on the cricket ball and it flies away to the boundary, right? So what was coming at, let's say it was a straight drive. To simplify things, instead of cover drive, let's make it a straight drive. The ball came 150 miles an hour and hit the bat. He provided a straight bat. It hit the bat and then it went back, right? Now, that short period of time, maybe, you know, 0.1 second or even less. Okay. But during that period of time, the ball hit the bat and then it rebounded. The ball is a rigid body, right? Doesn't change the shape. If the ball's shape changes, they get you a new ball, right? So now, during that period of time, integral FDT leads to a change, net change in the momentum of the ball. Okay, so that is the whole idea behind this. All right. So now dp by d. Now, if there is no external force, then momentum is conserved. That is a second rule from Newton's first law and second law. When you take Newton's first law and second law, if you say that there is a system of bodies, right, which don't have an external force, then you can say that its momentum will be constant. dp by dt will be 0 because there is no external force. Why is dp by dt 0? F is equal to ma. There is no F. If F is 0, then dp by dt will be 0. If dp by dt is 0, that means P is constant. Okay. P versus T curve, right? If P versus T curve is a flat line, its slope is 0. dp by dt is the slope. So if P stays constant, we say dp by dt equals 0. And if dp by dt is 0, there is an important word that we are going to use called conservation. If something doesn't change during the time over which we are observing it, we say it is conserved, right? My friends, who were not very active, everybody will be playing basketball during the lunch time. For some children will be playing cricket, some children will be playing other games, many different games in school, right? So many different games are there. So one of my friends, he will be sitting like this after lunch. He'll be sitting like this and watching everybody play. I would go and say, Ramesh, what is going on? No, you're not playing like the other boys. He'd say, no, I'm conserving my energy. So the thing is, when we say conservation, right? So that is what it means. That is, you're not expending any energy. So if something is conserved, it means that it is not changing. It is kept constant. Okay. So, so remember my friend Ramesh, when you solve problems involving conservation. Now you're going to do a lot of problems involving conservation of either momentum or energy. Now, related to the idea of momentum conservation is this idea of center of mass. Okay, center of mass, right, is typically an idea that comes into play when you have a system of particles. Okay, if you had one particle here, one particle here, one particle there, right? Now the three particles together will have a common center of mass. Okay. Now let us say that there is no external force, right? So if there is no external force, there is conservation of momentum. Okay. If there is conservation of momentum, the center of mass of the system of bodies will experience Newton's first law. So let me state this again. Okay. There is not one body anymore now. So far, we were looking only at one body. There are many bodies. Okay. So M1, M2, M3, M4, Mn. Okay. Now, between them, so this system of bodies, multiple bodies, are not experiencing an external force. They are only experiencing internal forces. There is no FEXT. FEXT equals zero. There is no FEXT. Okay. They are only interacting amongst themselves. If they are only interacting amongst themselves, the center of mass of that system of bodies will follow Newton's first law. What is Newton's first law? An object remains in a state of rest or in uniform motion, a straight line, unless compelled to change that state by an applied force, right? This, instead of an object, we are now going to be discussing multiple objects, and therefore we are going to say a system of objects remains in a state of rest or in uniform motion, a straight line, unless compelled to change that state by a applied force. Okay. So that is the main difference between what we were doing before and what we are going to be doing now. Now there is no longer one body. There are many bodies. Okay. Now the other thing is that, let us say I have one carom. In carom, I don't know how many of you have played carom. See, in carom they put one powder, right? And this powder, then they will use the striker and then they will hit the coin, right? Now, when the striker goes and hits the coin, it will deflect this way, deflect that way, etc. Right? So think of it that way, right? When the striker, first they will arrange that in the center, right? All the coins in the center, red in the middle, white and black around it, right? And they will use the striker and then they will hit the coin, right? If you go and hit it, everything will go 10 places, right? Now, the striker is actually creating an external force, right? So if you look at the system of coins in the middle, right? Why do they put powder? Powder is to reduce the friction, right? Now, when the striker is hit, right? It provides that external force, right? And so now all these coins arranged in a certain form, they go this way, that way, this way, that way, this way, that way. Okay? That is the subject that we are discussing today. Okay? Think of it that way. Okay? Now, the external force, right? In the case of the striker, right? So, initially, what is the momentum of all the coins kept in the center? Zero, right? What is the momentum of the striker? That is however strong your finger is, right? Strong. Some people have strong finger. Some people do this. Some people do this, right? So Some people do that, right? So based on how strong your fingers are, I don't know if people do exercises for the fingers to when they play carom. They must be, if you are a professional carom player, you want to be very good. Maybe people do some exercises. But anyway, so you hit the striker, right? So now who is providing the momentum? My hand is providing the momentum to the striker, right? The striker gains a certain momentum. Okay. Once the striker gains the momentum and you include the striker and the coins in the system, right? After that, there is conservation of momentum. I have imparted a certain momentum to the striker. Then from that point on, everything that happens involves conservation of momentum. Okay. So initial momentum imparted to the striker, it is moving. Weight of the mass of the striker times the velocity imparted in a particular direction on the board, right? So it goes and hits, and then all the coins move this way, that way, this way, that way, this way, that way, right? The net change in momentum is essentially provided by the momentum imparted to the striker. Okay. Now, why do the coins stop? It is because there is still friction. Even though you put so much powder, if the powder was so perfect that it will keep on, everything will keep on moving forever. Okay, and the sides were also without any were perfect collisions, right? It will just keep, all the coins will keep on moving, 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 moving. But there is friction, and the friction slows the coins and stops them. Okay, so part of the game of carom or golf or all these games, right, is to understand the nature of friction. Okay, and so we will discuss all these things a little more, but this is not a sports class. So the idea of center of mass, right? The idea of center of mass is like this. Okay, the uh, the center of mass of a system of bodies is like a weighted average, what they call the weighted average. It is called sigma mi xi by sigma mi, right? So xcm equals sigma mi xi by sigma mi. So it is, when we say weighted average, what we mean by weighted average, it is weighted by each mass. Okay, so if I have a big mass here and a little mass here, the center of mass will be much closer to the big mass, right? So let us say I have a straight line, 10 kilos, 1 kilo, right? So where will be the center of mass? It will be closer to the 10 kilos, right? So that is the summation that they do, sigma mi xi by sigma mi, right? Now, if this is at 1 and this is at 10, the 1 kilo is at 10, the 10 kilo is at 1, right? The net position may be at 2. Okay, so what is sigma mixi? This is at 1, 10 times 1, that is at 10, that is also 10 times 1, but it is the m is 1 and the position is 10, right? So the total mixi is 1 times 10 plus 10 times 1, right, equals 20. 20 divided by the sum of the masses, 10 plus 1. Okay, so 20 divided by 11, that is almost that is 1.8, something like that, right? So so that is how you calculate the center of mass. Okay, so it will be closer to the bigger body. Now, if you had a 3-dimensional or 2-dimensional space, then you will have a center of mass x and a center of mass y. So if I said there are 3 coordinate space, there is with an xy coordinates for each, the center of mass will be somewhere in the middle, like a centroid, right? If in a triangle you have this thing called the centroid, right? So the centroid of a body, right, will give you the center of mass. Most often, the best way to, let us say I give you this book or some, the center of mass should be here, right? Not necessarily. Let's say some parts are little bit heavy, some other part of the book. So how do you calculate the center of mass? You hang the book like this. Then you hang the book like this. Then you hang the book like this. Okay. You draw a straight line to the earth. The meeting point of all these straight lines, right, will give you the center of mass. We are making an important assumption that that is actually called the center of gravity, right? Center of gravity and the center of mass are mostly the same. They can only change if the gravity is not uniform. Okay, so but in most cases they are the same. Okay, so sigma mi xi will by sigma mi will give you the center of mass. Sigma mi gi xi divided by sigma mi gi will give you the center of gravity. Okay, so but I'm just giving you a distinction that those things come only in the context of when there is center of gravity is not there is non-uniform gravity. Most often there's uniform gravity, and therefore center of mass is there. Okay, now why is the center of mass important? The center of mass, the momentum of the center of mass is conserved. That's why it's important. Now, if you had a continuous mass, right? If you have uniform mass, the center of mass will be at the center, right? So if I say this is this book, right? The center of mass of this book is probably there, right in the middle. You take X and Y, it is very uniformly weighed, right? If it was not uniformly weighed, it may be lower, it may be higher, etc. Right? Now, now when you have to evaluate a continuous mass, right, instead of sigma mi xi, the equivalent using calculus is integral x dm by m, and m is integral dm. Okay, so integral x dm by integral dm will give you the x coordinate of center of mass. Y coordinate similarly will be integral y dm by integral dm. Okay, so that will give you the ycm. Okay, now this is an important idea you must learn, because we are going to introduce, when we introduce rotation, we will introduce its corresponding equivalent. Just like we said, there is angular momentum, angular velocity. Like that, there is a corresponding equivalent to center of mass, which we will be introducing then. So I definitely want you to learn center of mass, so that also is a little easy. So don't ignore the center of mass. Learn it well. Sigma mi xi by m, sigma mi yi by m, sigma mi zi by m. We will give you xcm, ycm, and zcm. All right. So here is an example. So calculate this is a two-dimensional example. There are three masses. There is 1 kg at 0, 0. There is 2 kg at 1, 0. This, right, 2 kg at 1, 0. And then there is 3 kg at half root 3 by 2. Okay. So 1 kg, 2 kg, 3 kg. Where will the center of mass be? Sigma mi xi by m. Right? Sigma mi xi by m will give you the x coordinate. Sigma mi yi by m will give you the y coordinate. Look at how he does the calculation. Then he calculates and says it is at somewhere here or somewhere here. Where is that? 7 by 12, 3 root 3 by 12. Okay. So this is if the three particles are form a unit equilateral triangle. So unit equilateral triangle means what? Every side is as 1. All the angles are 60 degrees. Therefore, from that he computes the point B, the point C, and the point A. Okay. So sigma x dm by m. Okay. So now he is doing the same for a uniform long rod. Okay. So for uniform long rod, the center of mass will be at the center of the rod. Okay. Now, but then if it was a tapering rod, right, that is it expanded like that, right? So then your x will what is that? dm is this. So x dm, right? So dm is this. Okay. How do you do this dm, right? So what is dm? Dm is the mass at a distance x. Okay. If the mass varies with distance, then it will have a different, dm will be different. So what you do is if it is uniform, right? If it is a uniform rod, right? At any distance, the dm will be a constant, right? What is that constant? It is like a density, right? The density is what? So the whole mass is, for if the whole length is the whole mass is m, the whole length is l, so m by l, right? So now at a distance, so dx will be m by l dx. dm will be m by l dx because it's a uniform rod. Okay. Now, as it went further, if it got thicker and thicker and thicker, okay, it was thin here, it became thicker and thicker and thicker. Okay, like I don't know what. Sometimes there are different kinds of things. Okay, it will be thin here and it will be thicker and thicker and thicker. Okay, or if it is curved, right, like a sickle, sickle will be curved, right, or or it is a say a knife shaped like that, right? So those things will have this differently shaped values. Therefore, the center of mass will be further down. Okay, so then what you do is, at every distance x, you calculate the corresponding length. Okay, and then you evaluate the dm will be not m by l dx, but it will be proportionate to the length there. Okay, what is the length there? That will be x times something. Okay, x times m by l square dx. Okay, so or some equivalent. So there will be, let's say it has a slope, right? So you must evaluate that using calculus techniques. Okay, so you may not get such questions, or you may get such questions, particularly if you're a JE student. So you must learn the maths around that, and we will do one problem, involving that. Okay, not too many, but we'll definitely do one problem. But that's how you evaluate. So at a distance x, what is the length, right? You get a measure using simple geometry. Okay, and so you will then have, instead of m by l dx, you will have m by l times k times x dx. Okay, so there will be an extra x term, and when you integrate, it will become x cubed by 3. Here it is x dx, it becomes x squared by 2, and then you put x equals 0, x equals l, right? So correspondingly, you will end up with a value which is not l by 2. It will be further down. If it is shaped like that, it will be further down the body. Okay, so and so that is how these are evaluated. We will be looking at moment of inertia when we look at rotation. That will produce a different answer. That's why I'm readying you for that. Okay, so now the motion of center of mass. Okay, so now we are going to derive the theory around this, right? So we have n bodies, each at a vector. So remember that we are always in the realm of vectors. Okay, now center of mass is a position, and therefore it is a vector, right? So the position of the center of mass in this case is that vector, is a vector that points from 0, 0 to that position. That position is this 7 by 12, 3 root 3 by 12. So it is 7 by 12 I plus 3 root 3 by 12 j. That is the position of the center of mass. Okay, so now, so position vector. So now the center of mass r is given by the position vector rcm, which is equal to sigma mi ri by sigma mi. So we evaluate, right, center of mass as a vector, it's a position vector. Okay, so so you have an x component, you have a y component, then you put xi plus yj. Okay, and so we first did it in component wise, we separately did it, and then we looked at it. But you can also do it with using vectors in a vector equation. Okay, so now if you differentiate both these sides, the and when you differentiate both these sides, what are you saying, right? You're saying that the center of mass itself, let's say each of the bodies is moving, like in the carom board, right? The center of mass of all the bodies taken together also will experience, we already said, also is going to experience Newton's first law, right? The center of mass of the whole system of bodies is also going to experience Newton's first law. Okay, and if there is no external force, the momentum is going to be conserved, right? So now you take the derivative, right? Dr by dt will give you sigma mi dri by dt, right? If you take the derivative of both sides, right? What are these dri by dt's? That's merely the velocity. What is the left hand side? That is the velocity of the center of mass. D capital RCM by dt is the velocity of the center of mass. What you see, the small dris by dt is the velocity of the individual bodies. So the velocity of the individual bodies, right? If there is no external force, the net dr cm by dt is going to be conserved. Okay, so now what he is doing is he is taking the m and he is moving it to the other side. Therefore, he has this mr equals sigma mi ri, right? So now when he differentiates, he gets m times dr cm by dt. So that is the mv of the center of mass. That will equal the mi dr1 by dt, m2 dr2 by dt, etc., etc., etc. So that is going to lead to the conservation of momentum equation. P equals P1 plus P2 plus P3 plus P4 plus Pn. Okay, because the left hand side is the linear momentum. M times dRCM by dt is the linear momentum of the center of mass. Okay, so the linear moment of the center of mass is going to be conserved. What does that mean? Linear momentum of the center of mass is going to be conserved. I hit the striker. I have imparted an initial momentum to the striker. That is the initial. All the other bodies are at rest. Okay. Now, throughout the motion, okay, if you take out friction, the striker is going to hit the coins. Many coins are going to go in many places, but the momentum of the center of mass of the whole system is going to be conserved. That's the whole idea in this motion of center of mass. It is a application of Newton's first law and Newton's second law into the idea of collisions. Okay, of this theory of collisions. It is a vector equation. It is a follow-on of the ideas you learned in kinematics and dynamics. All right. So that's how you should understand this. So mv equals m1v1 plus m2v2 plus m3v3 dot mnvn. Okay. Now, if you differentiate one more time, see, we differentiate both sides one time and we got the momentum conservation equation. If you differentiate a second time, what do you end up with? ma equals f1 plus f2 plus f3 plus f4 dot fn. That is merely Newton's second law. Okay, F equals ma. Okay, so so remember that. Now, what is happening in the context of the carom, right? The context of the carom, the forces that are between the coins, right? Because if you take the whole system, there is no external force once I hit the carom coin and then let it, say that, okay, now this has acquired a certain momentum, right? Momentum is conserved. The forces internally get cancelled. They may hit each other and fight, amongst themselves, right? But the forces internally are going to get cancelled because of Newton's third law. Every action has an equal and opposite reaction. A applies a force on B, B applies a force on A. If you count both the force and the reaction, the action, the reaction, all those internal forces will get cancelled. Okay, so this is a very fundamental idea that you must understand and learn. Okay, so there is conservation of momentum, in the context of and that's how you understand center of mass. Okay, and that's we reiterate this idea that Fext equals 0, then dP by dt is also 0. Therefore, P is a constant. P is conserved. Understand the meaning of the word conserved. All right. Now, I'm now going to introduce this new concept because today we are doing this new chapter, workforce energy. So I'm going to introduce this concept called kinetic energy. Kinetic energy of a body, of a moving body, right, is a scalar. Work, energy are all scalars. Okay, they don't have direction. They only have a magnitude. Okay, now when I hit the striker, right, the striker acquires a certain velocity. You all know that striker has mass, more mass than the coins, right? So now the kinetic energy of the striker is defined to be half its mass, 1 by 2 m times v square. Okay, 1 by 2 times m times v square, where v is the magnitude of the velocity. Okay, so you can say v dot v if you want, right? Half m times v dot v, right? Or you can say half m times v square. Okay, so half mv square will give you the kinetic energy of the striker, right? Now, the kinetic energy of a system of particles, right, under certain circumstances only is conserved. Okay, so we will be introducing work, power, and energy today, right? But you must understand that kinetic energy need not necessarily be conserved. I'll come to this calculation in the next class. Okay, this is the center of mass calculation. I will come to it next class. First, I want to introduce you to all the ideas that we are going to see. Okay, what is work? I introduced the term kinetic energy, right? Half mv square. Okay, what is work? Work is something that is done by a force. Work is the product, is a scalar product of the force and the displacement. You all know that force is a vector. Displacement is also a vector. Okay, the product of the two, or more importantly, the scalar product of the force and the displacement gives you work. Okay, now if I apply a force, okay, I am going to use my hand to push it for a certain distance. Okay, so I am applying a force and I am applying it over a distance. F times d, right? The distance over which I apply this force, F times d, will give me the work done. Okay, now typically, right? So now when I do this work, right, I am also, what I'm doing is I'm counteracting the friction, right? Friction is also doing some work in the other direction, right? Now, but if there was no friction, the work that I do, like in the horizontal direction, will change the kinetic energy of the form. If there is no friction, it will change the kinetic energy. Okay. Now, so those are the basic ideas of work and kinetic energy. Now, there is another thing called potential energy. Potential energy is, you know, like it's one of those things that is, how can I put it? It's not a real thing. It's a difficult thing to say, you know. It's when we say it's not a real thing, right? Like, when people say, he has potential, right? This boy has potential, right? That means he's going to do very well in life, you know. Oh, that boy has potential. Some teachers will say, oh, that boy has potential. That means that he's going to do very well in life. Or that girl, she's very, very good girl, has potential, right? So that means they're going to do very well in life in the future. Okay. Now, similarly, when we say potential energy, right? Potential energy is can be viewed as something that can be converted into more or other forms of energy. We say electrostatic potential. Tomorrow we'll be discussing electrostatic potential, right? So when we say electrostatic potential, we will be discussing the potential of students, or not students. Electrostatic potential is the potential that is that you get as a result of an electric field. Okay, so because of that, we have to try and make sure that that we do justice here. Okay, so let us continue to make progress with this material. Okay, so we introduced work, and we introduced kinetic energy as half mv squared. We introduced what work is. Work is done by a force. It is the force multiplied scalar product of force and the displacement, right? F dot dx, right? Will give you the work. Work is a scalar. Work leads to the change in the kinetic energy or the change in the potential energy. Potential energy can be considered as the capacity to do work. Okay, now see, I take this cell phone and I move it a certain distance. Okay, now this cell phone, when it comes down the same distance, it loses its potential energy, right? Now, if I drop the phone, right, from this, I take the cell phone, I have moved it up, right? I have done work, right? F dot dx I have done, right? Now I let go, right? What happens to the phone? Its velocity increases and increases and increases up to the point where when my hand applies another force to stop it, right? So it goes faster and faster and faster, right? So as it goes faster and faster and faster, right, there is the latent work that is done in raising is lost and converted to potential, converted to kinetic energy, right? So when I lift it up, people say that it has potential, acquired potential energy. That means it can later be, as it drops and comes back to the same position it was in, it will acquire a different form of energy. It's called kinetic energy. Now, the ability to do work, the potential to do work is also there in the case of electrostatic potential, right? So in an electric field is very similar to gravity, right? See, this is, I'm doing work in the context of a gravitational field. Okay, so now we will electrostatic potential, potential energy, gravitational potential energy, etc., right, are only defined in what are called conservative forces. Okay, now we will discuss conservative forces also a little bit down, because we're going to spend several classes dealing with this subject. So we introduce work, we introduce kinetic energy, introduce momentum, and then we say that at some level these are all quite intertwined. They are not related, but they are intertwined. Okay, and you must learn each in its own box, right? Every Tirukural you learn, I don't know, in Tamil, when I studied Tamil, they used to teach many different couplets called Tirukural, you know. Now, every one of them would teach a concept, okay? Like that only you should learn physics also, you know. You should learn each concept separately, but together they will make a whole. Okay, so that is the idea in physics. You should learn it in singular detail, but all the details are in fact related. You know, so work, power, energy, force, momentum, etc. They all come together in, and of course the vectors, calculus, they all come together in a unified whole. Okay, there are many subjects that are like this. Okay, so but when you learn physics and you learn the intertwining of all this, then you are in a position to learn other subjects also. When you learn biochemistry, you know, and you learn biology, and then there is, you know, the intermingling of biochemistry, biology, all these subjects, they come together into a unified whole. You cannot learn, you cannot say anatomy is different from physiology, you know. Anyway, I will not talk so much about biology because I want you to go and attend Professor G.K. Bhatt's lectures and then learn biology there, you know. But many subjects are involve related concepts. Okay, so chemistry you learn Tiwari ji, and G.K. Bhatt ji you learn biology, physics you come to me, then maths you go to Tarun. Okay? Tarun is asking for students also to come to his class. Just attend. You know, a very good maths teacher is a joy to listen to. You know, learn good maths also. Okay, and then it will help you also when you have to take the exam. You get good marks. You know, it's always very good to learn a new subject very well. Okay? So work power energy. Work done by a force is in displacing a body through a displacement x is given by Fx cos theta. It is a if the angle between the force and the displacement is between 0 and 90, right? Cos theta is positive between 0 and 90, right? If it is 0, it is 1. Cos theta is 1. If it is 90 degrees, cos theta is 0. So if the force and the displacement are orthogonal to each other, or perpendicular to each other, then the force does not do any work. Okay? Let me give you the classical example of when force does not do work, right? When force and displacement are perpendicular to each other, that is when a body is moving in uniform circular motion. Body is moving in uniform circular motion. What is the direction of the acceleration? Radial, right? What is the direction of the force? Radial, because the acceleration and the force have to be in the same direction. Newton's second law, F equals ma, right? So centripetal force, centripetal acceleration towards the center, right? What is the direction of the motion? The direction of the motion, the direction of displacement is tangential. So you have Fx cos theta, right? So if it goes a short distance, F dx, right? The dx is tangential. Velocity is tangential. Okay, so Fx cos theta is therefore what happens to Fx cos theta? F is like this, dx is like that. So F and dx are perpendicular to each other. So there is no work done by such a force. Okay, so very tricky idea, but it's a true idea. Okay, now related to work is this thing called power. Power is the work done per unit time. dW by dt is power. Okay, so power, it is also F dx, right? So it is F dot V. Okay, if there is a constant force, it will become F dot V. Okay, so so note that, so we will discuss power later, but right now we want to discuss only this. When the work is done by a constant force, you just bring the it becomes just F dx, and it depends on the angle between F and dx, right? Because dx can be changing, you can be doing all kinds of forces. The body could be moving in different directions, right? So f dx can be changing, right? The dx could be changing, right? So the angle could be changing, right? Now, in addition to that, the force itself can be changing. The position is changing. The force itself is changing. So we need to use techniques in calculus to evaluate the work done by it. The area under the S, if you do an F versus X curve, the Y axis is F, the X axis is dx, then the area under the F versus X curve will give you the work done. So when you have to calculate, you can break it up into, as you know, you can, to calculate the area, you make little segments and then you add those segments to find the area. That is called integration, right? So what is the calculus you need to find the to do f dot dx? It is integral f dot dx. So integral f dot dx will give you the work done is the area under the force versus x curve. All right. So with that, I'm going to stop for today so that you can go on to attend other lectures. Thank you for attending today's lecture, and I hope to see you again next class. Tomorrow again we have our class, so let's continue with tomorrow we have the electrostatics, Gauss law. We'll continue with that. All right. So thank you for attending, and I'll see you again next class. And keep at it. Do more problems. Unit 1, Unit 2. I have done started with some problems. Do more problems. Every class, do more problems. Soon you will become start feeling more comfortable. And as time goes on, you will be readying yourself. Whether you're taking JEE exam, whether you're taking NEET exam, you'll be readying yourself, and you will gain the benefit of what you're doing. From all the learning that you get, you will always be gaining. Thank you.